Welcome everyone, welcome back. We took a 2-week break, but now we're back for the MAMNA virtual seminar series. From now on, we have a very exciting lineup, and I will let Ryan, co-president, tell us who we have the pleasure of hosting today.
So hello everyone and welcome back. So today we have Professor Rebecca Taylor, who is an assistant professor of mechanical engineering and by courtesy of biomedical engineering and electrical and computer engineering at Carnegie Mellon University. She received her bachelor's degree in mechanical engineering from Princeton University in 2001. Dr. Taylor earned her Ph.D. in mechanical engineering with a minor in bioengineering from Stanford University in 2013. Professor Taylor is the recipient of the NSF CAREER Award and the Air Force Office Scientific Research Young Investigator Program Award. And so Professor Taylor, I'll hand over the floor to you.
Thank you so much. Okay, so I want to let everyone know I'm so happy to be here speaking with MAMNA today. And so I am a mechanical engineer who I think a lot of people would say just wants to make all the things. And in particular, I'm interested in making structures that have features at many different scales. And so what that means is we use sort of unique combinations of both self-assembly and then sometimes top-down, what we call hybrid, top-down, bottom-up manufacturing methods. And the examples I'll talk about today have to do with both nanobiosensing and robotics. And I guess if you have questions along the way, you can put them in the chat, and I know we're going to have a Q&A afterwards, but I can also answer them along the way if anything's really confusing. Great. So just sort of getting details out of the way, if you end up wanting to learn more, I want to say my group is the Microsystems and Mechanobiology group at CMU. And if you want to find us, I just recommend you search for MMBL and CMU or my name Bex. So that should get you there. So that's our group. And sort of as Ryan so kindly put, basically, you know, I had training in mechanical engineering. And I think the things that are really interesting is, like, I was interested in robots, you know, as an undergrad. And also I had an industry career. So I worked as a mechanical design engineer for about 5 years before coming back to academia. Likewise, for anyone who is ever found that they suddenly got interested in something very late in the process of their education, I realized how interesting I thought biomedicine and bioengineering was about halfway through my PhD. And it's not too late to, you know, make big changes. So I want to encourage people, if you find this interesting, I wholeheartedly support you changing directions and reach out to me to, you know, learn more about what we do. And so I think that my background really sets me up to be interested in making tools across scales, because I've worked at the macro, the micro, and now the nanoscale. And I really see myself as a product designer. And so I think that's sort of an unusual approach for what could be a nanotechnology person. Like, really, we're making systems, and it's not that we want just nanostructures. We want materials that have features across the scales, because that's how you get interesting behavior, right? And so the motivation I would use ever so briefly is, if you think about the human heart, you know, it's going to undergo as many cycles as like a high performance 2-stroke engine in its lifetime, and it never gets to stop. And I'll try to stop the video so it stops the beating sound, but it never gets to stop, and it's even if it gets damaged, right? And so that's phenomenal functionality. And all the way down, even at the nanoscale, you have molecular motors powering that activity. And so what this says to me is that as an engineer, we want to be building complex systems, but the structuring at every size scale is incredibly important, right? So mechanical engineers in particular, I want to emphasize, should think about nanotechnology, because we want to give nano features to macro and micro systems. Okay, cool. So in today's talk, I really want to talk about 5 things. So my first goal is to convince you that DNA is boring. In fact, DNA is an engineering material, right? My goal is it's good if you think it's boring. You should think DNA nanotech is fascinating by the end. But the first thing is it's an engineering material. And then we're going to talk about uses for DNA in both self-assembly and then these hybrid methods. Great. So let's get started with this. So for those who are unfamiliar with DNA nanotechnology, I have little labels down in the lower left corner, and those are just Cliff's notes. Like, what do you take away from the slide? These things are small. They're biodegradable. They're biocompatible. And really, you put the pieces together. So usually it's either all short DNA sequences or one long scaffold and many short sequences. And if you cool them slowly, they can form an ordered structure that matches what you design. Okay, so that's what I'll refer to as like sort of DNA nanotechnology, DNA origami. What's cool is that there are many pieces, but it's very much like a Lego process. You put the pieces together, you run the anneal curve, and then you can get your little person out, you know, or whatever structure or machine you're trying to build. And so this is something that mechies in my lab, you know, do every day. And so it's not, if you're not familiar with bio research, molecular biology, this is not particularly challenging. I wish I could spend 20 minutes on this slide, but I won't. But what I will say is, when you think of like enzymes, sort of like nature's nanomachines, I think about globular systems. I don't think about stuff that looks like a chair or a laptop or a 4-bar linkage. And DNA nanotechnology has this very, very strange property that, due to its geometry, we can build rectilinear structures with it, right? And so when Paul Rotermund invented DNA origami, really he revealed a sort of biomaterial that allowed unprecedented control over both precision and also the types of shapes you make. So our intuition at the macro scale is actually really useful for building DNA nanotechnology. You can build square lattice-based structures. Honeycomb-based structures actually like don't have much inherent twist at all. Like when you put them in solution, what you build is what you get. And so anyway, and it's all based on the fact that the helical structure allows basically one helix, double helix, to see its neighbor at different points down its length. And they're about 10.5 bases per turn. And you can use that to weave structures together, right? So also people that are interested in knitting and weaving, DNA origami is a delightful avenue for this sort of thinking. And I just want to say that this is all by way of an intro. There's CAD, right? And so as an engineer, you know, we're trained to represent 3-dimensional systems in 2 dimensions. And there's actually software for you to design these structures one strand at a time so that you can actually build legal structures that you can then synthesize, or you can design and then synthesize. Cool. Okay, so, oh yeah, other things. It's basically hard plastic. When I talk to people, the 2 takeaways I'd like you to have first are that DNA is boring. If I can convince you we understand it, we can predict about how it's going to behave. If it's boring, then you can just think of it as one more engineering material that you have in your sort of engineering toolbox. And the other thing is that it's basically hard plastic, right? And so then those are the 2 things I want you to know. It's going to have like effective Young's modulus on the order of like hundreds of megapascals. So that's pretty useful in a biological environment where things are pretty soft. And it can be useful in general when working with soft materials. Okay, so the next thing is sort of one of the first applications I want to get you thinking about, which is just that polymerizable nanotubes can be nanoscale actuators. All right, and so here we have a video of Listeria monocytogenes, and they're actually invading a host cell and then polymerizing actin behind them in these tails, and then the actin tails end up depolymerizing. But you actually have an organism that is like pushing its way through the cytoplasm and just sort of like pushing things out of its way, cutting through, all through the action of like a tube polymerizing, right? And so the mechanics of tubes is really interesting because forming them is basically like creating an engine, right? And the tubes that you form, depending on their cross-section, depending on how the molecules are interconnected, they can have different stiffnesses. And so here are some example biofilaments. You have the very stiff microtubules, and they're kind of like, you imagine like the hard spaghetti in the cell, you know, whereas you've got the actin filaments, which are very floppy. So these are materials that are really interesting to think about when we want to imagine what building with DNA might be able to accomplish. Okay, and basically polymerization and depolymerization are foundational. They're critical to locomotion, cell adhesion, as well as force sensing and cell division. So I'm really interested in filaments. Okay, now a topic that I want to talk about with DNA nanotechnology is, I said these things can be rectilinear, right? And here's a really beautiful example. If we design like panel A on the left, a nanostructure, as like Dietz did in 2009, if you have 10.5 bases per turn in your design, which means that on average, between crossovers that sort of link your regions of your structure together, if you have about 10.5 bases, then, or 10.5 bases per turn, then you're going to have an unstressed structure, right? It's basically just going to be linear. But now if we have regions that are too short, right, where basically on average, you actually are having the crossovers spaced more closely, and it's about 10.5 or 10 base pairs per turn, you can actually see that you now have a twisted structure, right? And it's a left-handed helix. And this comes from the fact that DNA is right-handed, so if you have too little, you get a left-handed torque, right? So you can get twist, and you can do the same and get with having too many bases and get a right-handed helix, right? And so you can actually control the level of twist. And in the same paper, they showed you could independently control bending as well. So there are ways to make fixed structures that are both twisted and bent. And for people designing machines, that's incredibly useful. There have also been studies showing kind of hollow nanotube type structures utilizing the same principle, right? So if you've got a region that has sections that are too short, you can get these like left-handed helical structures, or you could have regions that are too long and you can get right-handed helical regions. And what you would get, the result shown here in these TEM images, is that you can have either like sort of linear looking filaments that are just elastic filaments. And then here you've got these kinked ones, right? So it looks like they've been crimped. And this is because they actually have helicity to them, right? So one question our lab asked was, if it's possible to make static structures that are twisted and bent, what does it take to make them dynamic, right? And so then I guess what we decided was there's probably almost an infinite number of strategies that we could use in order to dynamically twist or bend the structures. And we came up with one reversible approach for doing this with DNA nanotubes. So here on the left, you see we can make a DNA nanotube and we can decorate it with gold nanoparticles, sort of distributed along its length. And the scale bars here are 100 nanometers and 20 nanometers in case you can't see them. Okay, we can also make structures that are twisted. And the evidence of twisting is that you see those little gold nanoparticles switching sides. So they go from staying on one side to switching sides. And what we decided was that if we build pre-stressed systems, we could then use a strand displacement reaction to release that stress. So you could imagine that you could form a twisted tube, like a helical tube, and then pull off all these regions that are applying the pre-stress and allow the tube to relax. And so here we actually have demonstration of the fact that we can switch back and forth. So with the same batch of tubes, depending on which fuel strands we introduce, we can twist and untwist. And so what we're really excited about is now we've got a nanomaterial that can twist and apply force, and it may be able to contract. So if you were pulling on your environment, for example, that twisting and contracting could be used to help you assess the mechanical properties of the medium that you were in. And this is one of the things that we're really interested in doing. It's using these sensors to gather information about the environment in real time. And currently in my lab, 2 of my students are extending this project to go one step further. we've got nanoscale actuators, and we would like to have the actuators tell us what conformation they're in. So imagine that the tube itself changed its fluorescent properties as it got untwisted or as it got stretched, right? And so both Tito and Sebastian are now working on these like nanospring sensors using a really high-tech concept, which is that of a lever, right? So they're trying to do like the amplification of a displacement so that they can get a sensitive fluorescent readout of a sub-nanometer deflection. So I'm happy to ask questions about this later, but essentially we're trying to get to the idea of having a smart material even. You could embed these in a material where it could tell you how much either force it was experiencing or how much strain it was experiencing or how the stiffness varied across the system. So this is like what we see is really interesting. It's like kind of bringing the nanoscale into microsystems and macro systems. Okay, and so these are all kind of like little bite-sized stories. So there's another story I want to tell, and it has to do specifically with what happens when you put that sort of self-assembly bottom-up fabrication together with top-down fabrication. And it has to do with microswimmers. And so my collaborator, Matt Travers, and I, we were curious if we could make an articulated magnetic microswimmer with dimensions in just the order of like a few microns, right? And so theoretically, a system like this could swim through, say, the capillaries, like the smallest capillaries in your eye, or through viscous media in your eye. And that the idea is that the whole robot is less than 10 microns across. And so for scale, and maybe this is the MAMNA community, you know that your hair is about 80 to 100 microns. So our goal is that this little microswimmer is at most 1/10 of the diameter of one of your hairs. Okay, so this is our first investigation, making robots and learning how to make monodispersed systems from polydispersed components. Right, here they are swimming again. And so we have a red blood cell for scale, which is the smiling mouth. And that red blood cell is actually bending as it's sort of squeezing through the capillary. Okay, so in general, microswimmers are really interesting. So they could be used as biosensors, for targeted drug delivery, for sort of micro manipulation, moving things around, for microscale mixing, and potentially for microsurgery. All right, so they have many applications in manufacturing as well as microfluidics in medicine. Okay, and so this is a project that's that my student Emma Benjaminson has been working on. And so here we have fiducials that are the circles that aren't moving in this video. And then we've just got little clusters of magnetic microspheres. Ooh. All right, and when placed in an oscillating magnetic field, so it's approximately constant magnitude, but it's oscillating around a heading, you can see these little microswimmers skate around, right? And so then they're pretty cool, right? The diameter of each bead is somewhere between 1 and 10 microns, and we can purchase them with a given size, and we can functionalize them so they stick together and make robots that can move around, right? But then the question is like, you know, as someone very interested in manufacturing and pushing the limits of how we make things and enabling us to ask new questions and, you know, attain new capability, I would look at this and say, first off, it's amazing that it's moving, but there are some major drawbacks. I won't be offended if you've seen them, right? They're not all the same. I can't control what size the cluster ends up being, how many beads there are. I can't control what, you know, if there's a connector between them, how long it is. So it's hard to see how you would get from this to like an organized microsurgical robot system. Okay. So the first thing we want to talk about is how they're connected. So one thing we could potentially do is connect them and tune the stiffness of their connection, right? So instead of like gluing them together, what if we connect them with those same sorts of tubes that I talked about from the previous project, right? So we've got a flexible tube, we know what its cross section is, and we can functionalize it so that it can connect two beads, right? And so in this case, we're going to buy streptavidin encoded beads and then decorate the DNA with biotin, which will then have like the strongest non-covalent bond. Strongest ionic bond in nature, attaching the bead to the origami. Okay. Little bit of background for those interested in robotics. I want to talk about why it's really hard to be a very small scallop, right? So if you are a scallop, at the macro scale, life is pretty good, right? So you're open, you close quickly, you force liquid out, you go shooting forward, right? Okay, so here's what happens for a scallop at the nanoscale or at low Reynolds number, right? So you may displace liquid and you may move, but then when you open back up, you go right back to the starting point and then you displace and then you come back, right? And the reason that this happens is because at low Reynolds numbers, sort of the ratio of the inertial forces to the viscous forces goes way down. So inertia is not really helping you anymore, right? So in order to locomote, you have to get around what is called the scallop theorem, which is at low Reynolds numbers, you really need to break the symmetry. And so if you think about like flagella rotating, if you get like a periodic wave through a system, all those approaches break the symmetry and allow you to swim. So we would like to build a system that is not stuck and not constrained by the scallop theorem. I mean, you can see that the swimmers in the previous slide are already moving. So there's something we're doing already to get around this. Okay. And I want to talk just a little bit about control, right? So we know the structure of double-stranded DNA. We know the structure of the nanotube or approximate structure of the nanotube that we're building. So we can start describing some of the structural properties and the mechanical properties of our connections, right? And what we found through modeling was that actually the stiffness of that connection does matter, right? So the stiffer we made our connection, like the more like just a rigid fixed joint we have, the lower the velocity, right? And the more flexible, the faster the velocity. So if we can control the stiffness of our connection, then we can actually modulate how fast these swimmers could swim, right? Okay, so that's one really big opportunity. So something else that you probably noticed in the first video, and I'll play this one so you can see it now with some tracing of those particles. When we have these sort of randomly formed microswimmers, they can move. They can violate the scallop theorem. They're not symmetrical. They break the symmetry. And this external magnetic field also allows us to put energy into the system to drive them. So they're going to move, but they're not all moving in a coordinated way, right? And as someone, if we're interested in microsurgery or mixing or robotics, the idea of having a swarm that's all very uniform has the potential to allow us to control the directions and have all those directions be the same, right? And so then in order to move this capability to the next level, what we really need to think about doing is creating technologies that allow us to control the body plan. Okay. All right. And so here is where I introduce you to templated assembly via selective release, and also where I glow about what is possible with the nanoscribe and 2-photon polymerization. Okay, so fundamentally, here's a method that was developed by the Livermore lab, which utilizes some sort of template with hemispherical pockets. And then you shake it, right? And if you have microparticles, microbeads, that have surface energy matched approximately to the material that you have that's pocketed, then you can actually have beads come and settle in those pockets. And if they're a bad mix, if they're a bad match, the kinetic energy just forces them right back out because you're shaking, right? But if they're a good fit, then those surface forces hold it in place. So the particles that fit well can stay in place. And in that way, you could actually say, put a small one here, put a big one here, put a small one here, right? Okay, and so one of the key things about making a swarm of micro robots is that we don't know the best strategies to control them, So what we'd really like to do is have a method that allowed us to make microswimmers in sort of a rapid prototyping fashion. We don't have like tape out and then 6 months to wait. We want to be able to make a new batch of swimmers like every day or every 2 days. And so we can adjust both our control strategy and our design iteratively. Okay. And this is where two-photon polymerization comes in. And here's a picture of the Taj Mahal. It's, with a 200 micron scale bar. And then I like these spooky spiders that, 6 of them could fit across the one of my hairs quite well. And so it was interesting that while I was doing a postdoc in a biochemistry lab, the world of MEMS just sort of took off. And suddenly you could make microscale polymeric unsupported structures like really easily. And so I agree that I think with many people in MAMNA that like, this is a really fantastic technology. And so one application is, let's make some pockets, right? And so for us, here's just a demonstration of, we'll make hemispherical domes and then mold PDMS off of them. And then that PDMS can be our pocketing mold. All right, and here we have SEM just showing that we've got these nice hemispherical pockets. Even though the resolution is on the order of like 400 nanometers, it's really smooth. And so we have nice sort of conforming pockets to what we hoped for. And then just to show that this technique works with a PDMS template that's been made from a TASR derived mold, we did some size selectivity measurements. And so I talked a little bit about like, what do you want out of a robot? And we really want a robot that has sort of a uniformity in its control. So one thing you want is that when you say, I want a bead that's say 8 microns, you really want that size. So we then did a test where we introduced a population with many different sizes of beads and pockets that were intended for 8. And what we can show is that we can kind of sub-select for just that size, right? So that's a good demonstration. Furthermore, what we also showed was here at the top, we've got this sort of wide distribution of bead sizes, but we can actually tune the size of our pockets and select out different subpopulations from this one, right? So you have a polydispersed input, but you've got a much more tightly grouped output, right? And so you can see particularly the interquartile range went down threefold for the outputs. So here we have some really powerful size selectivity. And what that means is we can make patterns of rumballs. And so on the left is just an example where you've got a 10 micron magnetic bead surrounded by 3, 6, or 8 micron magnetic bead. That's, maybe I'm off, maybe it's 12 and 16 magnetic bead. But yeah, and then here's pictures of rumballs because I think they're delightfully similar. But here we're showing we can arrange these. Okay, so then I've been taking more time than I wanted in this talk, but I wanted to show you some swimmers swimming around. Yeah, so here's the one that really matters. So here are 2 bead swimmers, and it contains a big magnetic bead and a little non-magnetic bead. And when we put it in this oscillating magnetic field, sort of off it goes, right? And so if I play that again, you can see this. And what's interesting is they start kind of far apart, right? And so this is actually a demonstration, not only that it's swimming, but that we built an elastic connector between the 2. And to sort of back that up and give you more information, when we rotate this guy in place, we actually see that the beads kind of unfold, or stretch that elastic element between them if you're just doing a rotating magnetic field. But once you start doing your oscillating magnetic field, they pull back together and then sort of scoot off with a known velocity. So we've done, and the separation when they're apart, I should say, matches the separation they had in the template. So this is a demonstration that we can control the mechanics and the sort of structural dimensions of elastic connections, enabling complex body plans in micro robots. Okay. Yeah. So we're really excited about this and sort of investigating multiple different body plans and trying to basically do what I think is most exciting is build uniform swarms of these robots from polydispersed components, but somehow get monodispersed out. Okay, and so I really just have one more section to get through. I want to take a little detour to just get you excited about DNA nanobiosensors. So the field of dynamic DNA nanotechnology has just really taken off, particularly in the past like 7-8 years. So instead of making static structures, we're now making many more machines, and machines that look like macro scale machines, machines that use different forms of actuation, machines that work with proteins and peptides. And so this is just a tremendously exciting area for the development of actuators and as well nanobiosensors. And so my lab, a major focus that I'm not talking about is we're interested in mechanosensing. So we're interested in making sensors that can actually read out forces, and forces on the piconewton scale, but even the sub-piconewton scale, right? On the scale, sort of the thermal fluctuation energy. And so this I'm happy to talk more about, but I think it's a really exciting area when we think about responsive materials and integration of these into larger scale materials. I think is going to lead to some really exciting technological advances. Also for nanobiosensing, DNA origami in particular, but just in general, DNA nanotechnology allows some really cool capabilities. So we have a review at the bottom. I recommend if you want to check it out. It's the only nanomaterial that allows you to pick your bioanalyte completely independently of the transduction mechanism that's going to allow you to get a signal out, right? And so this can be really potentially powerful. And so, yeah. Ask questions or give me a ring if you're interested to talk more about nanobiosensing. But the last thing I want to talk about is, as a advanced manufacturing researcher, I'm really interested in DNA because it is essentially a programmable adhesive and it's got sub-nanometer resolution, but it's not the only information-bearing polymer out there, right? And so we did some research into using a synthetic mimic of DNA called peptide nucleic acid. And we've been building nanostructures out of these materials. And so here also, I should say, my student Shriram Kumar has worked on both the actuating nanotube, nanosprings, as well as our PNA tubes research or nanofibers research. And he's a phenomenal researcher, and he's wrapping up his PhD right now. And so I know he's going on the job market. So I think if you are all interested in gamma PNA research or dynamic DNA, I want to suggest a fantastic candidate. But yeah, so PNA, the thing what you need to know is the figure on the left. It's similar to DNA, but different. It can bind DNA. It's less twisted than DNA, right? There's 18 bases for every turn. It's really easy to functionalize. One of its superpowers is that the enzymes that degrade DNA and degrade proteins, peptides, they don't touch PNA. So it sort of has potential to be a really interesting Trojan horse molecule. Also, if you want to make sensors that work for a long time, it's not going to break down as well or easily. So it has potential uses there. It can also be left-handed or right-handed, which allows for some interesting sort of computation opportunities. But really, it binds DNA, and it binds much more strongly to DNA than DNA does to itself, right? And then the final thing that's really interesting about it is it has no problem hybridizing in organic solvents. So there are these organic solvent mixtures that would typically lead DNA nanotech to come apart. This may not pose a problem for PNA, therefore expanding the range of environments where we can use structural nucleic acid nanotechnology. Okay, so this work recently came out in Nature Communications. And so if I breeze through it, I highly recommend you take a look at it. But essentially we had, as mechanical engineers, it was really fun because we had a structural challenge. We had a molecule that had different geometry, right? So if we wanted to make a structural motif for weaving, like literally a weaving approach for this molecule, it had to be different from the approach we would use for DNA. Furthermore, there's a practical constraint in how long these oligonucleotides could be. And so we used really short ones, like 12 bases. And so there were huge geometric constraints, but we came up with a system that would create structures that were not largely pre-stressed. And so we made these 3 helix nanofibers. We showed that, you know how I said it binds more strongly to itself than DNA does? Well, we showed that the thermal stability of about 6 base interactions is better than like 10 or 11 bases of DNA. So we could get away with short sequences. And then we have a structure that allows a 2-domain, what they call single-stranded tile motif, to work to allow us to form tubes. So if this program, because literally the thing at the top is a program, if this program works, it should form a periodic structure. So we're not going to see a finite size system, we're going to see a long filament. And that's great because it's easy to see long filaments, right? And so sure enough, in fluorescence microscopy, we see these filaments, and I apologize for the lack of scale bars. These scale bars are 5 microns. So this filament is longer than like, you know, on the like 9 to 10 microns. And these are some of the longest we saw. Typically we'll see, you know, many in the range of a few microns, right? And then when we did TEM to sort of zoom in, we saw something surprising, right? Which is that these things are really fat and variable. So unlike DNA nanotech, which tends to give you these really monodisperse, like the circumferences are always exactly what you planned, ours appear to bundle together. And we got some verification when we sort of zoom in and we see alternation of tight bands or alternation of light and dark regions. And then these are consistent with what we think would be the diameter of our tubes. Okay, so we could build tubes, but these are really acting like what they are, which is not a DNA and not a peptide. There's something in the middle. So there's something interesting about these structures. And we also found, you know, that we were hoping to play with twist with these structures. And what we found was when we selectively introduced DNA instead of PNA, we thought maybe that over-twisted nature of DNA would allow us to twist our structures. But we saw the very opposite. We saw what looks like a massive stiffening. So this is definitely the sort of like uncooked spaghetti model. Massive stiffening of our structures. And it happens with 1, 2, and 3 kind of to the same extent. So this is we're really excited about this phenomenon. And we don't see it when we have a substitution of a strand that functions differently. For the strands that cross the helices, introduction of DNA makes the system more likely to aggregate and actually kind of makes it less regular, more appropriate for like a surface coating, right? So we basically see huge, interesting questions and maybe some really novel applications for PNA. And then because it's not just like DNA, we showed that we can learn some lessons from proteins. So if we introduce a surfactant SDS, we could show that we could actually break up these filaments. And you can see we've got like sort of thick clusters, and then it gets thinner and thinner, and you can see like this is much more, it's not quite monodisperse, but it's a much tighter distribution of diameters. And so we can see in this histogram below that we can break them up and actually see individual filaments and then probably like 2 filaments or 3 filaments stuck together. And so this is a new building material, and we are really interested to figure out its mechanics, to see how to use it, and to use it in processes that are not just nanoscale. So we want to actually work across scales. And with materials like this that don't have the same degradation limitations of DNA and that can be used in organic solvents, yeah, we think that there's a lot of really interesting manufacturing ahead of us. So in summary, I hope you think that DNA is boring, but that DNA nanotech is fascinating. So I hope I've done my job there. You've seen the power of polymerizable nanotubes as actuators. You've seen an example of hybrid top-down, bottom-up engineering for microswimmers. You're interested to learn about mechanosensors and other nanobiosensors. And you now have been introduced to the world of PNA as a building material. All right, and with that, you know, I don't really do any of the work. I feel like my grad students have done such a spectacular job with this. And so in particular, I highlighted Shriram, Ying, Mitchell, and Emma's work. And so I want to thank our funding sources and all our collaborators, and thank you all for listening. Sorry I went on a lot longer than even I planned. All right, thanks.
Awesome, thank you so much. That was a really, really great talk. So we have some questions from the audience, and so we'll make our way through some of those. So the first one comes from Emmett Freeman, And so the question is about the annealing process for the DNA origami work. And so the question is, does that process, the annealing process, work the same way it does for like steel or for glass in terms of relieving internal stress and improving structural integrity?
Oh, that's a great question. And I kind of wish I could go back, but I don't want to mess anything up. So annealing in this case, you end up, what you want to do is separate out all the pieces, right? So you want to denature everything. You heat it up to about 90 degrees C, and then you slowly cool it. And so, yeah, this allows you to basically have mismatches or to have certain strands of DNA bind each other and bind, but not bind well, and still have enough energy to let go and search for another partner that's a better fit. So it's a way, basically the longer you anneal, if you find the region where you have a melting temperature where it's like kind of all coming together then or all coming apart then, you could spend more time there. And then kind of what you're saying, it can work out the errors, right? So you can improve the yield by playing with that anneal ramp. But ultimately, the goal is to build what you designed, right? So there's not much benefit in having errors. It just like kind of makes your structure more soft and more likely to aggregate and not function like you wanted.
Great.
Yeah.
So our next question is from Ambika Somasundar. And the question is, how would a magnetic field be applied in the body, such as in the eye, in the example that you had mentioned?
Oh, this is great. Do I have, I wonder if I've got a useful picture of the Maxwell coils. I don't, but so the way, we're imagining that you might want to harness the power of an MRI. And I don't have a picture here of our setup, but essentially we're using Maxwell coils, and it is going to generate like a highly uniform magnetic field in the center. And at least the strategies that we're really interested in, and actually my student Emma has a paper coming out at IROS, and essentially what she's shown is that you can use a uniform field and then switch that field back and forth and allow a magnetic microswimmer to navigate, right? So you could imagine putting this near your eye, like having like coils around your head, or putting it, if you had it in your arm, coils around. And then the whole question she's challenged with is, how do you reduce that switching time so that you don't cause peripheral nerve stimulation? But we're actually exactly trying to figure that out. The current MRI setup it seems like a great test bench for strategies that allow for novel locomotion strategies for microswimmers.
Great. So the next question is from Brendan Henrihan. And so the question is, what are the applications of the ultra high sensitivity force sensors?
Ooh, yeah. Okay, cool. So we actually, one example that I think is fabulous is if you like camping, you think about like those tents that you can just sort of like toss and they pop up and it kind of assemble on their own, right? So platelets in your blood are a lot like that. They are just waiting for mechanical stimulation that will tell them that there has been some sort of damage to the vessel and they should stick to the wall and they should close it off, right? So the mechanics of the platelet is fascinating, but also they're responding to very, very small forces. And when I say very small, I mean like sub-piconewton, right? So I'm doing research with a researcher at the University of Arizona, and we're going to put nanosensors on platelets. And our goal is actually to measure those forces and to understand how the mechanical stimulation of those cells leads to their activation. And I think in many cases, we'll make, I think, so that one thing is like measuring forces that are so small that you never thought you'd be able to access them while they're being experienced. But also, if you just think about sort of limitations of say MEMS sensors, they might be on the order of like 100 or 200 microns, right? But if your particle is 2 microns, you have to have a nanosensor to integrate onto microsystems, to sort of instrument microsystems or even instrument microswimmers. And so we just want to extend the capability so that you're not just measuring like the wall shear stress, where you could actually sink a MEM sensor into the wall of a channel. We want to put little sensors exactly where we care about the forces. So I'd say that's one application. And typically I would imagine just in general, lighting up the surface of a cell, or it allowing you to get a window into like what cells are feeling, what tissues are feeling, how they're tugging on each other. Those are avenues that we're really interested in. But I think with that question, I would say like, turns out that biology is like largely mechanical. So there are just sort of unlimited applications.
That's really cool. The platelet example, I don't know if you've seen Nate Snidecki's old work.
Yeah.
Washington. What's the ailment that he was targeting? But it was supposed to be like a sensor for like, I think people in an emergency situation to figure out if they were if too much blood was gonna leave their body, or if they were going to clot properly. But yeah, something similar.
Like the von Willebrand factor or the whatever. Yeah.
I can't remember exactly, but it definitely reminds me of some of that work. But like that was based on micropost arrays. This is even like, you know, an order of magnitude more hardcore.
Well, it's like, and I think it's a great example of a complement, right? Because it's like platelets operate at the micron scale. So if you have a cluster of platelets working together, that's what they're all going to fit together to sort of stop the bleeding. So you want to have sensors that can measure these like multi-micron level forces. But at the same time, when it's still one platelet and you want to know how it's getting activated or how it's integrating into these larger systems, I think it's just really cool to think that we could measure at many scales and get confirmation.
Yeah, I definitely agree. So our next question comes from Walter Smith. And so the question is, for the microswimmers, can you get them to all swim in the same direction by starting with a DC magnetic field and then applying the oscillating field?
So I don't think we have tried that, but I essentially will say I will ask my student to try. But in general, I think that the problem comes from the beads themselves are going to align to the field, right? So as long as you don't remagnetize them with that DC field, the fact that you then apply the oscillating field should reorient them. And I think the problem that we're dealing with is that they're not all magnetized in the same direction, right? And so we need a little more fine control over that. But this is exactly what we do in lab. So I would say also, if you're interested to join our lab, please reach out to me, because we're basically doing exactly what you're describing. Is we're trying to figure out what are the routines that might modulate these swimmers' behaviors, and then trying to identify what part of our rapid prototyping process is responsible for variation.
Great. And so a follow-up question is, are the two sides of the PNA double helix held together by the same kind of hydrogen bonding as DNA? And if so, how can they hybridize in organic solvents?
So PNA by definition is an uncharged molecule. We think that there are like interesting surface. So I guess what I'd say is it's not totally clear to us what is different about our structures forming versus what's different with what people have seen with previous duplex studies. But there are, like all hydrogen bonds, right? There are these interactions with your solvent environment, right? So it doesn't because PNA is uncharged and you have the same nucleobases, the hydrogen bonds are sufficient to form it. So what we really showed is that it's because they bind more. Yeah, actually, I don't really know. That's it's a fantastic question for like, it's the same nucleobases. And I don't have a really clean explanation for what it is about DNA that makes it not form in organic solvents, because it actually can hybridize in organic solvents. It's just that the organic solvents destabilize it, right? But the hydrogen bonds are still capable of forming. They're just modulated, right? So what you see in our image is that DMSO and DMF do actually reduce the thermal stability of the PNA. when you have like 2-part and 3-part structures coming together, but it's not enough to make them come apart. Whereas with DNA, you would need like much longer strands in order to get sufficient thermal stability. So I think it's just wrong that I would say that DNA can't come together. It's that for DNA nanotechnology, we use DNA of a certain length, and that isn't stable in organic solvents.
So we actually do have other questions, but we're a little bit out of time, and so I don't want to keep you here for like the next hour. But there are questions in the chat if you wanted to comment, potentially under the chat or in the comment section afterwards. But in the meantime, I wanted to thank you again, Dr. Taylor, for coming for this talk. I also want to announce, so we have Professor Michael Saylor from UCSD, who will be with us next week, discussing treatment of infections with self-destructing, self-targeting nanoparticles, which is likely somewhat, hopefully related to this talk, actually, maybe. But I think that'll be exciting as well. But thank you again, Dr. Taylor, for spending so much time with us. And we'll see you all hopefully next week. Okay. All right. Bye, everyone.